Now, we are in the new age that no one asks about, do you understand quantum mechanics? Now we focus on what can you do with the quantum mechanics. The new concepts, such as entanglement, superposition, interference, now can be used to improve technology or change the paradigm of current technology. For example, the concept of entanglement, which can send the information faster than light, now using the telecommunication and also create an extremely sensitive sensor. So this shows that the left side is the quantum teleportation actually using entangled photon satellite in China. So they are actually in the satellite, they using the entangled photon, send the information, and they can encrypt the information using the entangled photon. On the right side is using interference pattern. They can measure the gravitational wave from the faraway black hole. So this concept, entanglement, interference, and superposition, now we can use this one to also create the next generation computer called quantum computer. From here, my rest of the talk will be focused on the quantum computation. The beginning of the idea started with Richard Feynman in 1982. He found one of the problems that if we want to model the quantum system with our computer, it is showing the exponential slowdown. Because of the superposition and entanglement, make the problem really complicated. So I will give you an example. Let's say there's some simple statistical toy model. We can generate binomial distribution. So the ball will drop from the input and decide to go to right or left with a 50% probability. And after decision, it will iterate the decision that going right or left, back and forth. And then it will reach to the basket. And when you look at this basket, we'll find this will follow the statistical distribution, binomial distribution. This can be simulated with the computer without too much problem. However, let's try with the quantum particle. The problem is that when the quantum particle decides right or left, it does not decide. It will go both together. So when it goes, it will go right and left together with a 50% probability. And at the second stage, it will go again, again, and again. It's even hard to make PowerPoint animation because now it just gets complicated. I cannot even make the animation. So this becomes really hard problem to solve in the classical computer because now it start superpositioning and interfere each other. So this becomes really difficult problem to solve. And actually, Scott Aronson and Alex Arkhipov showed that the problem is sharp p-hard complex class, which means it's a really hard problem to solve in the classical computer. And this makes exponential time. It needs exponential time to solve by the classical computer as you increase the size of the iteration. So how can you do it? The easiest way to solve the problem is actually just doing with the quantum particle. We just send the quantum particle to the double slit and triple slit and quadruple slit. We just repeat this experiment multiple times and measure what the result is. Then we can just get the result without using the computer. So we cannot simulate this problem with the classical computer, but we can experimentally just do it on the top of the table. So we can use the quantum system to simulate a difficult problem. So when Feynman suggested quantum simulation in 1980, there was an undergraduate student in Caltech was inspired by his lecture, and he came up with one of the ideas that can compute the prime factorization, which is number theory problem. So prime factorization is a difficult problem to solve using the classical computer. Let's say you want to calculate how to factorize 21. This is easy. Computer can show that it's 7 times 3. But let's say we try to factor out a larger number, something like 32 quadrillion, 193 trillion, 216 billion, and 510 million, 801,043. Well, computer can, we just blow the computer. It's a hard problem to solve using the computer. Because of that, people apply this technique to secure our privacy in the internet. This is called RSA encryption. Let's say I send a message to my girlfriend, encrypt by the RSA 2048, and send it to my girlfriend. Theoretically, if somebody wants to read my message, using all the computer in the world to decode the message, it will take us 3,000 trillion years. So when somebody reads my message, me, my girlfriend, and you already died, and universe already died. Sad story. However, when you use the Shor's algorithm, the problem is actually solvable. So if you have a perfect quantum computer, we should be able to solve in 8 hours, which is not that fast, but it's solvable. You can think about our security, such as banking and military, is all encrypted by the RSA 2048. This is very dangerous technology. Therefore, many governments start showing interest toward making a quantum computer due to the security concern. So, basically, there are many quantum algorithms that can calculate the problem much faster than our computer. And a quantum computer is a platform for all the quantum simulation, quantum algorithm can be done. This is why there's a many interest to building a quantum computer. And now, from here, if you understand so far, you did a really great job. But I will go slightly deeper into the quantum computation, so I might lose some of the people from here. So there are many different ways to realize a quantum computation, such as a quantum circuit model, 1A quantum computation, and others. I will focus on the most widely used model, which is a quantum circuit model. Before I go to the circuit model, let's take a look at the classical circuit. Here, we have a 5-channel. So we have a 5 bit of information. And as you increase the wire, we increase 1 more bit of information. Let's prepare some input state. 1, 0, 1, 0, 1. 1 means that I send the light. 0 means that I don't send the light. So now we put some logic gate into the circuit, such as NOT and OR gate. So this gate depends on my input signal, change the output signal. For example, if I put a NOT gate, if I send a 0, it will emit 1. If I put 1, it will emit 0. And I use this combination of these NOT gates. I can make addition, subtraction, multiplication, etc. So I only need to find this right combination of the gate to calculate using the classical computer. So let's say some simple example. Let's say I want to find the password of the bike lock. Of course, there's a better algorithm to find it, but let's say we just find the simplest classical computer example. So in order to find the password of the bike lock, we need to try all one by one. So check this one, check that, and say we try all the combination until we find a good lock, correct lock.